Hello, everyone. Welcome to another edition of the Focus on Geothermal webinar series. This webinar series is a partnership between ThinkJ Energy and Enerchange. I am Carlo from ThinkJ Energy, and I'm very pleased today to be hosting a webinar with the GRE-GEO team. So this is an EU-funded research project that is focusing on the development of glass fiber reinforced epoxy for geothermal applications. So this is a very innovative and interesting topic for me personally. I'm very much looking forward to what the project has produced so far. We have a very big panel today. I think it's the biggest panel we've had in this webinar series so far, but we're going to start off with Carlos Escobar, who is part of the consortium. He is the business development manager for Europe for Future Pipe Industries. He has a background in engineering from the Universitat Autónoma de Barcelona and has over 15 years of experience in the composites industry. We're going to start off, but for the audience, you are free to send in the questions. There is a questions tab in the webinar platform. You're free to write them in, and we'll get to them after the presentations. And so, Carlos, the floor is yours.
So thank you very much. Good afternoon, everyone, and welcome to today's webinar. First of all, I would like to extend a special thank you to Carlo Cariaga and the team of ThinkGeo Energy for providing us this platform to share some truly groundbreaking innovations in geothermal energy. Thank you all for joining us. Today, we are here to talk about something that is at the forefront of both sustainability and technological innovation in geothermal energy. The European-funded geothermal project GRE-GEO, which is paving the way of new glass-reinforced epoxy systems, also known as GRE, for corrosion-resistant geothermal casings. This is a project that transcends traditional steel, and it is something that we call it as the ascension beyond the steel, because that's exactly where we need to go, what we need to tackle, the challenges that geothermal sector faces. For decades, steel has been to a material for geothermal well casing. However, as many of you know from the experience, corrosion, scaling are reducing the lifespan of the steel tubular systems, which are crucial to maintain the wellbore integrity. This results in workovers, costly interventions that becomes necessary much earlier than expected. As a second option, one could try to solve by using sufficient resistant steel alloys tubulars, but both options impose a heavy financial burden on developers and operators alike. But imagine an alternative, a material that can be withstand this harsh environment without the same degradation over time. That's exactly what the GRE-GEO project has developed. A GRE glass fiber reinforced epoxy casing system using glass and carbon fiber couplings, especially designed for geothermal applications, to be used in accordance with the guidelines issued by the GRE-GEO, providing 4-quadrant service envelopes and related to GRE tubulars qualifications and procedures, along with a lot of verified information on scaling, wear, cementing, BOP, and installation tools, including an innovative developed belt-on. This is more than just an alternative to steel. It's a solution that offers longer lifespans, reduce an operational cost, and significantly lower the environmental impact. And this last point is key. We are not just talking about innovation for the sake of the cost of the efficiency, but innovation with a purpose, lowering the carbon footprint of geothermal energy production. GRE tubulars have a much lower life cycle assessment, which means a reduced environmental impact and embody CO2. This is critical as we push towards in a cleaner way, more sustainable energy solutions. In short, this technology not only benefits your bottom line, but also the planet. This project wouldn't have been possible without the collaboration of a multinational consortium of experts, each bringing unique insights to the table. The GRE-GEO project is supported by 8 leading partners, including Vulcan Energy from Germany, Dynaflow Research Group from the Netherlands, TU Claustral from Germany, Drilltech, also from Germany, ITA from Switzerland, Service Industrials di Geneva from Switzerland, Nuclear Research and Consultancy Group from the Netherlands, and finally, Future Pipe Industries from the Netherlands, the company I am part of and I am proudly represents today as part of the consortium. Each of these partners has been instrumental in developing a solution that is now being tested, being validated for the real-world application. We are confident that GRE will become the material of the future for geothermal energy. So first of all, let me introduce to Farid Siyof, who will provide us with his insights on the practical application of GRE in geothermal wells. Farid holds a bachelor's degree in petroleum energy from Qatar University in Baku, and later specialized in drilling engineering at TU Claustral in Germany. He began his career as a project engineer with GEO, a geothermal consulting company that was later acquired by Vulcan Energy in 2022. And today, Farid leads R&D department at Vulcan Energy, focusing on geothermal, resource and optimizations, and international research projects, particularly those within the European framework. His work has been crucial in advancing the GRE-GEO project, and he will explain us now today the innovative material that can mitigate corrosion and extend the life of geothermal wells. So please, Farid, the floor is yours.
Carlos, thank you very much for a very extensive introduction. I will be taking the floor and leading you through the main key points of the project and give you the overall overview of the project and what we have achieved in this 4 years of research. So the agenda of my presentation, my part of the presentation will be basically focusing on the market research, risk assessment, well design, and GRE compatibility of the existing oil and well used tools. So before we started our project, we had to perform a market study where we have looked at the available geothermal resources and see what is actually needed in the geothermal market. So what we have identified that there are quite extensive resources map in the EU, but however, some of the resources, although they are available for low and medium enthalpy, they are challenged by this higher salinity and a lot of byproducts in the brines. We have looked also in such kind of databases as NLOG to look through the well designs and identify the well designs that are the most suitable for our application. So one thing I should note at this point that our GRE product material can withstand up to 100 degrees. So its application in geothermal sector is limited or focused basically on the low enthalpy uses and can be extensively used in the heat pump sector. Given the natural gradient of the Earth, 3 degrees per 100 meter, we can actually point out that all well designs should be focusing maximum the depth of 3,000 true vertical depths, right? So our extensive work was from this point on revolving around well designs that had this similar architecture to the ones you see on the right side here. After identifying the zone where we can work and as well as the well design, we have started to work on the risks accompanying our new material. And since the material was quite new, we had to do the whole life cycle assessment, starting from drilling completion, operation, down to the abandonment. And this has led us to develop a very extensive hazard report, which included all things that were happening in the procedure or from the run-in back to the abandonment with all possible stresses, mechanical and actually operational loads. So the hazard table has looked at the potential damage sources from all the type and made a very extensive review of all possible effects and developed a series of mitigation actions to reduce the risks and increase the viability of the product and survivability in the field and real field applications. From the risks, after overcoming all the critical risks with mitigation actions, limiting it through the code and application guidelines, we move to the next step of designing a well. The well design started with the action table, and it has in itself a summary of multiple things, starting from all the loads that would be applying, seen in the hazard table, going to the material design, as well as such things as handling tools and safety were also included. The action table in itself looked at the lifetime of the well with different strings inside and looking to different key scenarios of applied loads. The loads are typical well loads throughout the lifetime of the well, and included also such cases as the kicks, water loss, pumping cement, and also buckling and bending during the run-ins and cementation. With that in mind, we have created an extensive list and could actually summarize all of that in the GRE liner design, which was our primary goal, to create a one barrier system with a GRE casing. On the right side, you may see the casing. It is in truth a combined well string, since the beginner, the surface level of the string is made in steel, and the subsequent strings are in GRE. And that's the advantage of it, because the fluid that is in contact with the casing will be out of pure GRE, thereby overcoming the corrosion and scaling issues. Additional advantage of this kind of hybrid design lies in the fact that down to 1,000 meters, it will have a double barrier design, given that the structure where the backbone of the well will be out of steel, and then the production casing will be out of GRE, thereby combining the advantages of both designs. Next, there's also a second option for the case where the well has already been completed. We've also provided a second design where we are going to look at the already existing steel design with the conductor casing and the production casing with certain 3/8, and then the liner, and then line it up with internal barrier with the GRE. This will, however, reduce a bit the internal diameter, but therefore the whole risks of corrosion, contamination, and scaling will be uplifted. This is very good for such reservoirs which has very high brine, the salinity in the brine, and also is prone to very rapid scaling accumulations. Moving further, the GRE compatibility. If we want to introduce this material to the market, we need to consider how can we actually use this material in the conjunction with already existing equipment. So within our project, we have also made a very big focus into integrating the material, the new pipe, into the existing API standard facilities, as well as the tools that are used in the field. This way, we will be able to have the smoothen the introduction of the new pipe and reduce the extra costs that are forced onto the producers through the using of unconventional tools. So our things that we looked at the different things. Here there are four main aspects. We have first looked at the performance of the pipe. which was in case of run-in, external and internal wear, then cementation, how strong is the cement bond with the new smoother surface of the GRE pipe. Then move to handling tools. And in the last but not the least, in order to consider the safety during the drilling and subsequent run-ins, we've also tested the pipe with the blowout preventer. So the wear, one of the questions that always rise up in this kind of subject is whether the GRE liner or even a pipe can withstand the wear, since it's not made out of steel. So we made this kind of a rotary tool setup in order to test the capabilities of the pipe. So in this darker red, you may see the piece of the pipe, whereas the rotating tool joint will be simulating, so to say, the internal drill string. We can also change these, and then we would be able to simulate the wear of the casing against the well walls. So the short summary of the all testing could be seen in this graph. And as you may see, in the water, the steel wear is actually one of the most biggest among all the tested materials. And if you look at the glass fiber in the water and in the mud with the presence of sand, we may see that the wear and damage to the pipe is minimal. And the reason for that is that the glass fibers are quite smooth and quite solid in order to withstand the wear effect of the string. Then we moved to the cement bond test. We made a separate setup for that one, and we have tested both internal and external cement bonding, and tried to push the cement through the pipe, or the pipe through the surrounded cement. And we may see here that the overall performance is a bit lower than in case of the steel, because we have a very big force requirement to push it through. In compared to the GRE pipe. However, the subsequent movement of the pipe within the cement will be then obstructed, which is not the case with the steel. Overall, the difference was around 30% less force needed for the GRE. And that is not very big of a difference in case of the cemented casing string. Handling tools. We have performed 4 different tests with safety clamps, spider elevators, hand slips, and slide door elevators. And overall, the whole performance has shown that the tools are compatible with the pipe if and when they are done in the sizes of the conventional steels, API steel grades. However, one of the advantages of the GRE is that we can optimize the wall thickness of the pipe to the given well design and the loads. So if you have, for example, a shallower well, you don't need a very thick wall pipe. So in that case, there could be some kind of deviations from the API external OD of the pipe. And in order to accommodate that, we have also developed a tool, a tongue, a belt tongue, that can actually effectively adapt to varying ODs of the pipe, and thereby effectively overcome this kind of a small predicament that may arise. The tool is, however, also viable for other pipes, and especially it could be applied for the alloy steels and the nickel and chromium steel pipes as well. So this is a very flexible tool that we have developed throughout our project. the BOP. The BOP testing were done in the two cases. We first tried to seal off the pipe and see how much pressure it can withstand. And as you may see, the sealing pressure has reached up to 104 bars, which is standard testing pressure. At well pressure, we have then tried to even increase the pressure, and it can withstand up to 156 bars. And thereby, it has withstood the standard procedures for the shut-in and seal compatibility of the BOP test. So with this, my part is over. If you have any questions, please address them in the subsequent section after all the presentations are done. Now I'm giving back to Carlos. Carlos, you can now present.
I can
Leo.
hear you.
Yeah.
Thank you very much for it. Very well conducted and very self-explanatory explanation what you have give to the audience. So now we move to the next panelist. The next one is Leo de Mul from Dynaflow Research Group, who will delve into the technical aspects of GRE casings, particularly how they compare to steel in terms of performance. Leo brings a wealth of experience, having worked for 25 years at Shell as a material specialist, where he focused on polymers and composite applications in the oil and gas industry, like, for instance, glass fiber piping, and HDP line carbon steel, and RTP, flexible reinforced piping systems. Since 2018, Leo has been with Dynaflow, where he and his colleagues have played a pivotal role in the GRE-GEO project, conducting due diligence on well design, performing finite element analysis, and reviewing materials compatibility. His knowledge of polymers in composites makes himself one of our subject matter experts from our GRE-GEO project. So welcome, Leo.
Okay, thank you, Carlos, for the introduction. Good afternoon, and thanks for the opportunity to show some of the results of our project. This presentation was prepared together with Kees Rokus from FPI. The topics I would like to discuss is the construction of the service envelope, the used test methodologies, the collapse behavior of downhole GRE pipe, and I will end with some conclusions and recommendations for future work. As indicated by Ferit, we used, say, a GRE-GEO default well, and Ferit already, say, provides some information on the components. So let's start with the service envelope. An important deliverable of the guideline is the construction of the service envelope for GRE, and I will discuss some of the challenges we had to address. Some points to mention are that the axial loads and external pressure loads are more severe for downhole casings than for surface piping. So there is a lot of, say, experience with GRE pipe and piping systems, but yeah, most of them are limited to surface laid piping and piping systems. The envelope verifications are based on both API and API 5C5. That is focused on, say, downhole steel tubulars, and ISO 14692. That is used for surface GRE piping and pipelines. The verification of pipe plus connector for casings is much more challenging than for piping and pipelines. Steel casing connectors are verified according to the API as indicated, and this is quite different and much more severe than specified for ISO 14692. So furthermore, the service envelope construction, we found that there are gaps between traditional surface piping and downhole applications. And that has something we had to address in the construction of the service envelope. In ISO 14692, only say 2 quadrants are defined. That's quadrant 1 and quadrant 2. In the IPI 5C5, we have 4 quadrants. In the IPI 5C5, the axes are also rotated and mirrored, and that makes it a little bit confusing for, say, people that are used to work in the downhole industry. So be aware of that. The ISO 14692 does not cover external pressure. So usually pipeline and piping systems are inherently resistant against vacuum conditions. So this was, say, really a big, say, challenge for this project. Also, say there is a difference in the duration of loading. So most severe collapse condition is short term, and especially during cementing, during the installation phase of the project. Say, if we looked at the resistance envelopes, in the GRE-GEO project, we looked at the construction for, say, low enthalpy wells, typically up to 95 degrees C, and focused on the construction of the following envelopes. So the ultimate service envelope, installation threshold and operation threshold at 95 degrees C, the installation and operation threshold at 65 C and for 25 C. Say the installation threshold and operation threshold envelope described in the guideline are mandatory, and for 65 and 25 C, these are indicated as optional. Say for the definition, we used say the following. For the definition of failure, we used damage development that leads to loss of integrity. And for the ultimate service envelope, shows, say, loads that result in irreversible materials damage that is typically, say, a catastrophic failure. So if you look at the construction of the resistance envelope, the ultimates, for the axis, we use the API 5C5 convention. So axial loads are on the horizontal axis and pressures on the vertical axis. So what you see here is the 4-quadrant initial ultimate envelope. Say the 2.1 point you see over here is found from internal pressure tests with cap end loads. The 1.0 point from internal pressure without end cap loads. Say the 0-1, that's from tests from using actual compression tests. The 0.1 point from actual tensile tests. And the -10, that is a calculated value for the theoretical compressive strength. That's why the lower part of the envelope is indicated by the dashed red line. So note that for the default well, the elastic collapse prevails. And this point is just a fictive value. For the threshold, however, elastic collapse will be used, as we will see later in this presentation. So if we then look at the threshold envelope, that's the black one you see over here. So the black 2.1 point you see over here is based on, say, long-term pressure tests according to ASTM D2992 at 95 degrees C. And this provides the regression gradient and the lower confidence limit. So the lower confidence limit is also indicated as hydrostatic design base. The black 2.1 point is also verified using a 1,000-hour survival test based on the regression gradient and the LCL value. Say note that say GRE is showing a degradation behavior. So this has to be taken into account, and that's why say we used this approach. The ratio between the 2.1 ultimate, so this point and this point, is used as a scaling factor for the actual tensile point, so the 0.1, and the actual compression point. Say the black -1 0 point is constructed using a 100-hour collapse survival test, and that is considered to be the worst case cementing operation. So for the resistance envelope during operation, we followed, say, the same procedure as for the installation envelope, with exception of the, say, -1 0 point you see over here, which is based on a 1,000-hour survival test, of which the regression coefficient is estimated from a parallel plate regression proxy test. The samples are taken from the 100-hour survival test, say discussed before, so that we cover the historical loads of pipes that have the historical loads the pipes have seen during the installation as well. The parallel plate test can also be used to estimate both temperature and time effects on short and medium term loading. Then something on the test methodologies. In the guideline, we have produced as part, as one of the, say, the major, say, deliverables of this project, we describe the traditional test methodologies for construction of the envelopes, like mechanical testing, as described in ISO 14692, but also in the API 5C5. And we also used, say, strain gauge measurements. Besides that, we also looked at non-traditional methodologies that are quite new to this industry, like the ultimate elastic wall strain concept. This methodology is currently under development in ISO 14692, and for composites with a 55 winding angle, there is quite some experience. For other laminate designs, this needs to be further developed. We also used optical strain measurements to measure the onset of damage initiation. For some laminate designs, we found a good correlation between the onset of damage initiation and predicted theoretical models. However, whether this holds for different type of laminate designs requires further investigation, but the results were very promising. I would like to show you a short video. Let's see if I can start this one. I think it's not possible to start the video, unfortunately. Oh yeah, it's running now. So what you see here is the optical strain measurement to detect the onset of the crack development. In this particular case, the strain was measured over a length of 7 millimeters. That's indicated by the line you see drawn on the pipe. And the standard deviation of the strain was plotted against the pressure and shows a linear development, as you see in the plot below. At the onset of the crack development, the line deviates from linearity, and that could be used as a threshold value. And this point was found to correlate well with classical laminate theory and failure criteria used. As you can see, say, if the loads progress, you see more and more, say, indications of material damage. And then something on the collapse behavior. When we started to test collapse behavior, we observed two different failure regimes that are also observed in steel casings. One is the compressive collapse dictated by exceeding the hoop strength, and this occurs at thick-walled casings with a low D/T value. In the plot, you see the collapse pressure against the D/T ratio. The red points you see over here are related to compressive collapse, and the fitted line is the line according to Lamé's equation. The elastic collapse indicated by the black points, so all the points are measurement points. That's the instability criterion for elastic collapse. And that follows the relation as described, for instance, by Timoshenko. The mode of failure in the transition area is uncertain. So I've indicated the transition areas by the horizontal and vertical lines. We used statistics to determine the transition area and decided that for the GRE-GEO guideline, we will limit the design to the elastic collapse region, indicated by the orange arrow in this plot. In this next slide, you see a typical elastic collapse pipe, or a pipe that has been subjected to an external pressure and failed in elastic collapse. This is one of the pipes we tested that exceeded the elastic hoop stability criterion until full collapse. The instability point is characterized by a sharp discontinuity in the pressure versus volume change recording during the test, as indicated in the plot you see here. We further observed that if the tests are stopped just above the instability point, unloaded the sample and reloaded again, the measured collapse pressure is comparable. So you see 3 test runs over here with almost, say, the same level of elastic collapse pressure. And that's also an indication that to a certain extent, this effect is also, or this mode of failure is also reversible. The characteristics of this pipe failure is a long longitudinal crack, as you see over here. And again, yeah, this is typical for an elastic collapse type of failure. So then, say the compressive collapse. The compressive collapse is a sudden catastrophic failure that occurs when the stresses exceed the compressive hoop strength limit of the material. In the displacement volume versus external pressure plot, the event is shown as a sudden drop in the point of failure. You can see over here. Here the external pressure is plotted against the displacement volume. And the characteristics of this failure mode is typically severe damage to the pipe, like the delaminations as shown in this picture over here. And you can also see the type of damage that is indicated in the picture in the middle. Say to understand the failure mechanisms we observed during the tests, we made extensive use of finite element analysis to explain the observed damage and helped us to adjust the design of the laminate to optimize it for, say, collapse resistance. Then I come to some conclusions. Yeah, the objectives of this project were to provide a guideline based on existing international standards like ISO 14692 and API 5C5 extended with specific GRE-GEO test methodologies. to develop an empirical analytical collapse pressure versus D/T prediction curve, accompanied by a critical review outlining the key areas for future research. The selected approach supports control of collapse behavior by tailored laminate design. We found an excellent correlation between the predicted theoretical critical collapse pressures and experimental results. Long-term collapse resistance is validated by both regression and survival tests at 95 degrees C. We included test methodologies relatively new to this industry, like UEWS and optical strain measurements, but concluded that these techniques still requires further research. The project provided also insight into the different collapse modes and the width of the transition area between these modes. And then some of the recommendations. The testing of pipe connectors is described comprehensively in the guideline, but requires further development. A broader use of new test methodologies like UEWS and optical strain measurements are expected to provide more accurate and less conservative threshold values, but also need some more testing and evaluation. In the guideline, the design is focused on casing dimensions in the elastic collapse regime. The use of tailored laminate design can improve the threshold levels to provide optimized products that are competitive and reliable. And this concludes my presentation, and thanks for your attention.
Thank you, Leo, for the presentation, which, although very technical, it was very clear and went straight to the points that the audience was surely expecting to hear. I would like also to thank Kit Rokus, who is also with us today, with whom Leo has worked side by side on this essential part. I believe that the chat function is activated, so feel free if you want to pose any questions. And I would like to remember that that those ones will be addressed at the end. Last but not least, our last panelist, Dr. Javier Holzman from TU Claustral, who will discuss the sustainability advantages for GRE casings, particularly in the terms of life cycle assessment. Dr. Holzman holds a Master of Science from the Academy of Engineering at the University of Buenos Aires and a PhD from TU Claustral. Since 2014, he has been the Chief Engineer and Drilling and Production Department of the Institute of Petroleum Engineering, ITE, at TU Claustral, and the Director of Fuel Scale Testing Lab. With over 2 decades of experience in the field, Dr. Holzman is recognized as an expert in the design and optimization of OCTG, oil country tubular goods, and has been a key figure in the testing and validation of the GRE casing technology developed in this project. Javier, the floor is yours.
Yeah, thanks, Carlos, for the nice and complete presentation. Yeah, last but not least, I will try to keep you alive until the end of the webinar. And let's say, yeah, let's start with my part. So I will try to divide the presentation in, let's say, 5 main chapters, some short introduction about the groundwork or motivation, to explain you the new challenges that we have to solve, some very short explanation about the traditional standards, and yeah, to describe also our new approach and make some conclusions and recommendations. Of course, at the end, we will have a round of questions and we will try to answer all of them. If it is not possible, our contact information will be also disclosed. Okay, so let's start with the groundwork that or the motivation. So currently, we phase out the moment that we start the project, also even before that, there is no acceptance on the use of a certain standard for downhole applications, composite downhole applications. Yeah? This was one of the first motivations, and second, there is a kind of lack of qualifications procedure for the 4 quadrants. As Leo Demule explained to you before, and Ferrit, we really need to qualify these products in all 4 quadrants and not only for internal pressure. Yeah? So our objective is to try to bridge, to try to connect two very wide and worldwide accepted standards. These are the ISO 14692 and the API 5C5, or the equivalent ISO 13679. The ISO 14692 is really focused on glass reinforced pipings, and the API 5C5 it's completely accepted for downhole applications. So somehow you have the two parts of the history, but they are not yet connected. And this is the let's say why we said, okay, rather than to start a fully new standard, which is an extreme big project but by itself, we will try to connect these two and to have a kind of short-term assessment for this type of product. The focus, as we mentioned several times during this webinar, is on low enthalpy geothermal wells. So the maximum temperature is 100 degrees or 95 for the testing. So we are not intending to go over that value, although it's maybe possible. So until that value, we know that this is more or less a kind of good product and at accessible prices. Like every time in life with new projects, whenever you have a target, you have to face some challenges. And I will try to mention some general challenges that we face at the beginning. Also some challenges related with the material behavior and the manufacturing. So first, the general ones. The first point that we have to mention is the design criteria. As you may be aware, if you are familiarized with downhole activities, everything is based on yield strength. Whenever you talk about steel pipes or metal pipes, you can, let's say, calculate all your resistance and envelopes based on the yield strength and the geometrical, let's say, properties of your product. Versus the so-called regression-based threshold for composite materials. In composite materials, unfortunately, they are more complicated. And then the more or less the equivalent concept is a so-called regression-based threshold or threshold. The next challenge is we are targeting to apply this in downhole applications, but downhole industry is not familiarized with this new concept, the threshold. So that's why this is also a challenge for us. Last but not least, the tailor-made casings and tubing strings. So for composite materials, in principle, you have an infinite geometrical combination of OD and wall thickness. So you can make thicker pipes, you can make bigger pipes, and you can tailor-made them for every single well. So this is also complicated the moment that you want to start some kind of standardization or qualification. Regarding the material behavior, there are some new numerical and empirical validated models are also under development. So we have developed a very nice collapse model, pseudo-empirical one. And there is one new standard, the DMV, which is extremely new and not yet accepted. So they are trying to develop and to relate some empirical validation models or numerical models that can be empirical validated. But we need to solve this now. So then our, let's say, idea is to perform a guideline. It's not a new standard, it's a guideline that is performance-based. It's a similar concept than the API 5C5 and the ISO 14692. The hot-wet conditions, these are also quite critical for composite materials. We cannot get into detail on that, but please keep this in mind. They can also be addressed in this kind of performance-based qualification program. They are very hard to be modeled. The last challenge that I want to mention is regarding manufacturing. So as you may know, if you are familiarized not with the downhole, but maybe with the composite industry, manufacturing and quality assurance process, it's extremely complicated. And therefore, you need really to take care of, let's say, the raw material, and also depends on the mill that you will use to manufacture your pipes, the seasons, etc. So this has to be somehow included in the guideline. I mean, it's a, let's say, a kind of, not a problem, but a kind of challenge that the industry has dealt with over the last years, and they know how to deal with that, but we need to include this in the guideline somehow. Then our idea is to propose a qualification per production mill, and also to recommend all type of pipe manufacturers that are targeting, let's say, to approach the downhole market, to include collapse test and tensile testing on the quality control program. So as I mentioned before, we focus on some traditional standards. I will shortly describe them. The ISO 14692, it's really focused on composite or glass reinforced plastic pipings, yeah, systems, but mainly in fittings for oil and gas, not in downhole. Yeah. It is really regression-based qualification testing, and it's also helping us to address the long-term validation. Unfortunately, it's only focused on first and second quadrant, which is, as we mentioned before, internal pressure with tension or compression. And the design envelope and qualification rules are focused, as I mentioned before, in pipelines and piping. So more or less in surface facilities, not in downhole. The ISO 13679, it's really accepted for downhole connectors, casing and tubings, but it's really focused on metal materials, not in composites. It's the main description. It's a really straightforward way to define a minimum design verification procedure and acceptance criteria. In order to do that, this standard defines different CAL levels, so connection assessment levels that are from 1 to 4. For our, let's say, application, these low geothermal enthalpy wells, we see that let's say, we may use the CAL 2 or 3, not the most severe one, but also not the most mildest one. And I will develop on that later on. It's a very practical way to compare different connections also. So if you qualify them, and I mean, from different manufacturers, and if you are a well-designed engineer that needs to design where to buy the connectors, this is a good approach to say, okay, these two connectors from different manufacturers may have similar performance or resistance. Everything is based on pipe body and yield strength, and the conditions, let's say the combinations of them in order to achieve a worst case scenario. This is more or less the philosophy behind this standard. Unfortunately, and this is, let's say, one limitation, I mean, if you think about composites, the time is not taken into account, yeah, and neither the loads during the lifetime of the well. This standard makes use of or defines mainly 3 types of series reliability tests. The series A, as you can see here, it's a 4-quadrant envelope that you have to go through all these points several times, clockwise and counterclockwise. The series B, it's only first and second quadrant, and you also need to move several times clockwise and counterclockwise. But on top of the axial load and the internal pressure, you have to apply bending. Yeah, that's why it's called series B. And the series C, it's only performed in the first quadrant, but this is more or less to simulate the type of applications that we are targeting. It's a so-called thermomechanical cycle. Yeah. So the idea is to perform several mechanical cycles and also to change the temperature in order to simulate somehow the loads that your well should be withstand over the lifetime of the well. As I mentioned before, we focus on the so-called connection assessment level 2 or 3. Very short. So the connection application level 2, it has a total hold time of 80 hours. And as you can see here, it's based on 2 samples. One of each will go, let's say, first through the series B. So as you can see in the right side, it's first and second quadrant. And then it will go to series A, yeah, at room temperature, all of them. And this is, let's say, in all 4 different quadrants, the series A. Yeah, the second one, it's only in first and second quadrant, series B. Yeah, at room and high temperature. So the CAL3 connection assessment level 3, it, as you can see, it's really much more demanding. So the amount of time that you stay in let's say, in the so-called hold period, it's 185 hours, which is quite long. As you can see, you have double the amount of samples. So we have in total 4 samples. And the main difference is, as you can see, if you compare this slide with the previous one, so you have also series A, B, but you have also the series C, and the series A, it's also at room, but also elevated temperature, which makes a very demanding procedure for the connector. So I will try to explain you our new approach based on the previous introduction, more or less. As you know until now, hopefully, if you get not sleep during the long presentation, we define the so-called failure envelope. That's already more or less defined. We have also the testing and the service envelope definition. Yeah, we have a new collapse pressure model and also the so-called, after that, the 4-quadrant threshold envelope. With all these parameters, our idea was to try to, let's say, to develop a guideline for a connection qualification test. Always focus on low enthalpy geothermal applications, yeah? So then we said, okay, let's try, rather than to make a new standard, to try to develop a kind of ad hoc test procedure that is based on the API 5C5 connection assessment level 3, yeah? As I mentioned before, theoretically, for this type of connection application level, you need 4 samples, but we will reduce this to 2 samples because of the type of product. There are some let's say, explanations for that. Make and break test, we will include that. Therefore, you need to really define the test procedure, dopes, torque, and let's say the quantity of make and breaks. The baking, this is a so-called baking, it's a part of the traditional test. We decide, let's say, to avoid that, not to make the product, let's say, an easier life or an easier path to withstand the test, but because of worst case scenario. So we know that the baking may help the product to withstand better the loads, first. And second, it's something that you can avoid because we will use water for all the tests. Yeah, so baking, it's really something that can be sorted out for this type of ad hoc test procedure. Yeah, and of course, as we mentioned several times, so we need to include the 4-quadrant threshold envelope in order to somehow define the test load envelope. So until now, you have seen the presentation from Leo Demule before. He really explained all the details to define the threshold envelope. But let's say to give you in one slide the main concept, I try to prepare this one. So the right picture that I am pointing now is the so-called tensile test that most of us should be familiarized with. And as you can see, it doesn't matter the time. Yeah? If your material has not, let's say, a hard corrosion, this tensile test should look similar after 5 minutes, 100 hours, 1,000 hours, or after 30 years of operation. Yeah. So this is why the steel, let's say, definition, it's much easier than composites. For the composites, imagine that we need to make the so-called regression line. So somehow we need at the beginning to define the yield strength, yeah, that you can apply over 30 years, is exactly that line, yeah. But in order to define that, you need really much more testing than the tensile test. This is just to summarize all the previous work, and this is our, let's say, kickoff point whenever you want to qualify the product. Also, to explain further why we select the CAL3, it's because of this. So if you check the full test matrix of the IPI 5C5, we really need to make testing on all 4 quadrants because of the service conditions. We also need to perform Series V, and we need to include some thermomechanical cycles. So we really point, let's say, or highlight the series that we need in order to qualify our product. And as you can see, it's a kind of mixture between CAL2 and CAL3. Yeah. But these 2 guys, so the thermomechanical cycle and the, let's say, the Series A at high temperature, is something that we think it cannot be avoided or should be in the qualification procedure. That's why we tend to move to that connection application level. I already explained before, there are some waivers. For example, maximum temperature in our case will go down from 180 degrees to only 100 degrees because of the material and because of the type of product that we are producing, that is water with maybe some remnant gas. We decide to change the pressurizing media from gas to water. It's also a worst case scenario. And this is more or less how it looks like, the procedure that we, let's say, propose to be followed in our guideline at the end of the project. Yeah. In order to perform this type of testings, I will not get in detail because I need somehow to wrap around. We, let's say, build up some, let's say, high pressure autoclaves, let's say, to characterize the material behavior. But the most interesting one is a so-called combined load frame. So we have also, let's say, design and build this nice frame during the project that is now operative and ready for, let's say, qualification testing. And this allows us to perform testing in all 4 quadrants. So the Series A, B, and C. Okay, so some conclusions and recommendations. So we all think that the most important deliverable out of this nice and long and demanding project is a feasible, a possible, a practical guideline for qualifications of composite casings for low enthalpy geothermal wells. Regarding the acceptance of these guidelines, so as you know, our industry is really conservative. So acceptance is always a big point, yeah. And that's why we prefer also, rather than to develop a fully new standard, to base our guideline on well-accepted standards like the API 5C5 and the ISO 14692. Testing of pipe and connector, it has to be mandatory. And let's say the most important part is to be able to define an envelope. And we also include this in the guideline, how to define this envelope based on our experience and also research. Further R&D, so research and development on new methods, as Leo Demule pointed before out. So we need to develop further methods. There are some methods that are, let's say, looks promising, and they may help us, let's say, not to define the threshold envelope now, but let's say to refine that and to, let's say, have not a better product, but let's say smaller safety margins that will improve the cost of the product. The qualification has to be performed per mill, fully traceable with product design, including winding angles, raw materials, saw fiber, resin, and sizing. That's extremely important. And yeah, the collapse and the tensile test to be included in the quality control program. Okay, so I hope you are still there and you may have some questions. So I will give my lead back to Carlos to guide the questions and answer session. Thanks for your time and for your patience.
Thank you to all the speakers. That was a very that was a lot of information, and that's very interesting. We do have a lot of questions. We'll try to manage through as many of them as possible. We probably can't go through all of them given the time that we have, but let's try to group them into sensible topics then. There are quite a lot of questions here on the testing done. So first question is on the wear test. So there's a question here that points out that during drilling, the drill string doesn't just lie against the wellbore. So there is significant impact as well during drilling. So was this impact force considered during the wear tests? And also during the wear test of the steel casing, was there continuous removal of the steel shavings done? Because I would assume this would accelerate the wear of the steel.
So if you allow me, I can try to answer the question. So yes, our test setup, I mean, there was no time to explain this perfectly, but this C-shaped section that you are, let's say, that is now in the screen, this is also moving back and forwards, which means we are continuously removing the chips that are coming out of the C-shape. The C-shape simulates the casing, and the cylinder, the rotating tool, it's simulating more or less the tool showing that. So the main idea is to try to simulate as real as possible the wear conditions whenever you drill the next section. Yeah. Keep in mind that our project was focused not on developing drill pipes of composite material, but the casing. Yeah. So I hope I answer your question regarding regarding the wear test. And regarding shock loads, no, we didn't simulate shock loads, but what we really take care of is to define a drilling program that will give you enough room, yeah, to avoid, let's say, getting stuck. And although you may get stuck, what we also find out after this wear test is that the friction factor of this material, it's really, really lower than the steel casing, which will help you in case that you get stuck to remove the pipe with lower loads. And also, this is a lighter material. So whenever you lose control or you run too fast your casing into the well, the shock loads will not be dramatically high. This is our expectation on that. Yeah.
Yeah. So moving to a more general question, then there's a question that points out that the drawback of GRE pipe used to be that to be able to meet the tensile or the pressure criteria required for geothermal, the GRE connections had to have a much larger OD. So was this gap something that was addressed by the research?
Exactly. So this is what I just mentioned. Yeah. So we really know that the coupling OD is bigger than the traditional steel casing OD. And therefore, the drilling cost is a little bit higher because you need to drill with, let's say, bigger ODs. But this is another, let's say, discussion, the life cycle cost analysis, which we are also doing, but the main focus on this presentation was on the technical part. Yeah. So I don't know if I answered the question properly. If not, you can reformulate the question. Yeah.
Xavier, one thing I would like to add that the FPI, the company, the supplier of the pipe, have developed the combined with a combined coupling, which is from inside is made out of GRE material, and outside the compressive and the hoop strength is given by the carbon fibers. So as you see on the picture, in comparison with the pure GRE coupling, the OD of the coupling of combined coupling has become significantly smaller. It is not comparable directly with the steel, but we could at least considerably reduce the excessive OD of the couplings. Yes.
I think that answers the question pretty well. There are several questions here on the interface between the steel and the GRE casing. So how is this handled? What type of completion is needed? What type of casing hanger is needed for just for this interface?
So we have not tested it per se throughout our project, but this kind of technology has been already used in the France, in Paris Basin. So there are actually, let's say, the transitional pieces that are especially made for this kind of transition between GRE to steel, and the hangers. The hangers for the liners are used a similar way to nickel-based and alloy chromium steel and casings. So there is a specialized pieces of the GRE steel transition, and they are taking care of this kind of these two material contacts. So this is already developed technology and applied and tested in field. Yes.
Okay, then another more general question is the GRE material suitable for deviated boreholes?
Yes. So I did not have enough place or time to show this, but it is actually very bendable. It is more bendable than say the steel, so you can actually have a bigger or bigger deviations of the well. But we have also in our whole project, we have tried to stick with API drilling standards. So we have tested against that. And as in the previous slide, the action table has also taken care of testing the bending loads against the whole string. So it's not going to be just one pipe, it's going to be the whole string that is bending. And we have tested that with a positive result.
Okay, then. A few more questions on logging. So can conventional logging tools be used for GRE casing? More specifically, there is a question here on the cement bond. So I understand this was tested, but how does GRE casing respond to cement bond logging tools?
Yes, so this is a very interesting question. The cement bond should be the tools that are testing the cement bond needs and require specific calibrations. So so if you take just an average tool, you might have some issues. Because you need more subtle calibrations against the GRE material. But for example, we have been collaborating with Schlumberger, and they said that if and when the certain level of calibration of the tool for the pipe is made, the cement bond lock are pretty much possible. But as I said, it requires prior calibrations. It cannot be done just with any tool. Right? It requires some minor calibration required.
Okay, but I guess the important thing is that you don't need a new tool for it.
No need. You need a specific tool and to calibrate that one, but it is available. It is available. So when you are speaking to service companies, you need just to inform them that you are using the GRE material. You might need to send them some samples for calibration. But besides that, you don't need an extra cost for some kind of completely breaking through new tools. No.
And then maybe one last question. This is also more on the compression testing of the casing. The question points out that body compression tests are normally done against the circumference of the pipe, not vertically. So I'm not sure if this was presented, but the question is, was this done?
Do you mean collapse test or?
Yes.
Compression or collapse? Wait.
I mean, we have done, or maybe I can, so maybe you mean local loading. Yeah, we have done some so-called parallel plate tests that we are using more or less to characterize the material. Yeah, we have done a bunch of those tests. We have done also, I think, more than 60 collapse tests in different diameters and wall thicknesses. So it's really a huge amount of testing, but what I can tell you is we really simulate all the critical loads that that this type of downhole application will see over the lifetime of the well. So
What
collapse,
was the question?
Yeah, sorry, Leo.
So
yeah,
was the question also related to actual buckling or say just external pressure?
I would say it's both, like internal and external.
So yeah, we tested both for external pressure and of course also for compressive loads.
Yeah. So the important point is not the, let's say, the numerical result, yeah, or the quantitative result. So it's more or less to set a procedure to use that to define a service envelope for the future, yeah, and the so-called threshold. And but yeah, as Leo mentioned, so we have tested all these type of loads. At the end of the project, there will be a lot of information that will be public. And if you need, let's say, to have any detailed information, you can contact us and then we can see if it can be disclosed.
Okay, then. There actually are a few more questions coming in, but I don't think we have the time for them. So for those who still want to ask questions, the contact details of the speakers are in the webinar, and we'll be publishing the recording of this webinar anyway, maybe in a week or so. And we will also publish follow-up material on Think Energy about the GRE-GEO research project, because this is something that we find very interesting. And so I think that's more than enough time. We thank you for all the speakers. Thank you for taking the time. Thank you to the audience for taking the time. We went a little beyond the usual time for this webinar, but it was a very good one. So thank you to everyone, and have a happy weekend. And goodbye.